Hello, welcome to my talk on elementary potential flows. This is the talk on the simple combinations of elementary potential flows, and some of the combinations can be used for solving some practical problems. So in this talk, we will see the uniform flow past the source, and then we will see the uniform flow past the 2D dipole. And for this example, the fluid pressure and the pressure coefficient would be examined. Then we will move to the uniform flow past the 3D dipole. And at last, we will make a discussion how we can solve the problem of a uniform flow past an arbitrary structure. The first example is a 2D source in a uniform flow. The source here at the origin of the coordinate, and the uniform flow with the velocity u0. Now the question is, what is the combination of the source and the uniform flow? Based on the superposition principle, the potential function for the combination of the uniform flow and the source can be given as phi, given as this. Here, u0x is the potential function for the uniform flow, and this part is the potential function for the source. Here, q is the strength of the source. However, for such a potential function, it is better expressed in the polar coordinate. Here, the transform relation between the Cartesian coordinate and the polar coordinates given as this: x equaling to r cosine theta, y equaling to r sine theta, and the potential function can be expressed as this. And this part is the potential function for the uniform flow in the polar coordinate. And this part is the potential function of the source. So we can easily calculate the velocity component based on the potential function. UR is given as the partial differentiation of phi with regard to r. So it is given as this. And the u theta is calculated as this. Here, UR is the radial velocity component, and u theta is the tangential velocity component. So once we have the velocity component, we can, based on that, the equation for the streaming function would be given as this and this. And we can solve the stream function psi from these two equations. And based on this equation, we can obtain the stream function psi given as this plus the unknown function f theta. F theta is the function only dependent on theta. And we can calculate this. From this stream function, we obtained this. And if we apply this equation, so we can obtain the differentiation of f prime theta equaling to this constant. Therefore, f theta would be given as this. Here, c is the integral constant. Now, if we assume psi is 0 when theta is 0, then we can obtain the stream function psi given as this. As we have shown in the previous slide, the potential function and the stream function for the 2D source are given as this and this. And based on this, we can draw the stream lines of the uniform flow past their source, see here. And we can conclude a uniform flow past the source is equivalent to a uniform flow past the bullet like the shape of the red line. So why this would be equivalent? That's because the incoming velocity comes to the source, and the magnitude and direction would change. See here. And there will be a boundary of these two flows, the incoming uniform flow and the source. The red line is a boundary for these two flows, which means there is no flow cross this boundary. Either the incoming flow would not pass the red boundary into inside of the bullet structure, or the source flow would cross the red boundary, come out through the red boundary. Therefore, there is no flow cross the red boundary. It is equivalent to the no penetration boundary condition for the incoming flow. That's why we say the uniform flow past the source is equivalent to a uniform flow past the bullet, the structure of the red line. The second example is 2D doublet or 2D diaper in a uniform flow. See this plot, and we will see what kind of flow we can get for these combinations. Again, based on the superposition principle, the total potential function phi would be given as this. This part is the velocity potential function for the uniform flow, and this part is the velocity potential function for the 2D dipole. And again, for this potential function, it is better expressed in polar coordinates, given as this. And here we use the transform relation between the Cartesian coordinate and the polar coordinate. And the velocity component can be easily calculated as UR, given as the partial differentiation of phi with regard to r. It is calculated as this, and U theta given as this and this. So here again, UR is the radial velocity component, and U theta is the tangential velocity component. Now based on the velocity components UR and U theta, we can build the partial differential equations for the stream function psi, given as this and this. And from this equation, we can obtain the expression for the stream function psi, given as this. And here we have an unknown function f theta. So combine these two expressions, we find f prime theta, the differentiation of f with regard to theta is 0. Thus, we can obtain the stream function psi given as this. Here, we assume psi equaling to 0 when theta is 0. As we already obtained the potential function phi and the stream function psi, here we use capital R squared given as this. So mu is the strength of the dipole and U0 is the uniform flow velocity. And then we can see the expression here, capital R squared divided by R squared. And the corresponding velocity component UR would be given as this and U theta given as this. Then we can, based on the stream function or the velocity component, we can draw the velocity vector in the field and the stream lines. Now we examine the velocity component on the circle of a radius of r. Therefore, on the circle r equaling to capital R, then we can obtain the radial velocity is 0, and u theta given as this. Therefore, on the sucker, the radial velocity is 0. It is equivalent to the non-penetration condition on the sucker. That means there is no flow outside the sucker passes through the sucker into the sucker, or the flow come out from inside of the sucker to the flow. And on the sucker, u theta would be 0 only when theta is 0 or pi. This would be the stagnant point. See the black dot. And we can also find the maximum u theta on the sucker would be 2v0 when theta equaling half pi or 3 divided by 2 pi, where the velocity would be the largest in magnitude. In this slide, we'll have a look at the pressure distribution in the flow for the uniform flow and a doublet. The general Bernoulli's equation would be given as this. However, for this example, the uniform flow past the diaper, it is a steady flow, so the first term would vanish. And in this example, we only consider a horizontal plane, so this term would disappear as well. And at infinite, we assume the pressure is P0 and the velocity would be U0. Then the Bernoulli's equation would give us the equation as this. So the pressure difference, it is given P0 minus P is the pressure decrease from the pressure at the infinite. It is calculated as this. And if we apply the velocity component UR and U theta into this expression, we have the expression as this. So this formula is correct for any field point except R equaling to 0. However, for practical problems, we might be only interested in the pressure outside the circle. We might not be very interested in the pressure and the flow inside the circle. In the previous slide, we have calculated the pressure difference. And here, we look at the pressure difference for the pressure on the circle when R equaling to capital R. So it is calculated as this and as this. Then the pressure coefficient Cp is defined equaling to P0 minus P divided by half rho U0 squared. So it is given as this. Now if we draw the pressure coefficient, we have the red line here for the potential flow. And here in the plot, we also plot the pressure coefficient for the real flow when the Reynolds number RE equaling to 6.7 times 10 power of 5. So we can see the biggest difference of the potential flow and the real flow would be at theta equaling to 0 or around here. That means when flow come here and the difference would be in here. This is true because in real flow, the flow will separate at the lee side of the circle. But for potential flow, there's no flow separation. However, based on the experience and the experiment data, when Reynolds number increase and the difference between the real flow and the potential flow will reduce. This is understandable because for the potential flow, it is inviscid flow. That means the Reynolds number is infinite. So the larger of the Reynolds number, the smaller difference between the real flow and the potential flow. In here, we can see two stagnant points on the circle where the flow velocity v would be 0. And this stagnant point would correspond to Cp equaling to 1 here, here, and here. When theta equaling to 0, the stagnant point is here. When theta equaling to 180 degrees, here or here, corresponds this point, theta equaling to 180 degrees or minus 180 degrees. Now in the example 3, a 3D doublet in the uniform flow is studied, and we will see what type of the flow will be obtained for this combination of these two flows. Again, based on the superposition principle, we have the total potential function phi given as this. This is the potential function for uniform flow, and this is the potential function for the 3D diaper. Now, the velocity potential function would be better expressed in spheric coordinate, which would be given as this. Here, the transform relation between the Cartesian coordinate x, y, z and the spheric coordinate r, theta, psi, given as this, and the potential function in the spheric coordinate is given as this. Then the corresponding velocity components are calculated as ur, defined as the partial differentiation of phi with regard to r, and u theta given as this, and u psi defined as this, and all this expression. Here, r cubic is given by this expression. Mu is the strength of the 3D diaper, and u0 is the velocity of the uniform flow. So based on the velocity component for the 3D diaper in the uniform flow, we can draw the velocity vector and the streamline. And if we look at the surface of the sphere, where r equaling to capital R, and we find ur would be 0. Again, this means there will be no flow across the sphere surface. The uniform flow past the 3D diaper is equivalent to the uniform flow past the sphere, and the sphere radius r would be given as this expression. From this expression, we can see the larger of the diaper strength mu, or the smaller of the uniform velocity u0, the larger of the sphere, because r is larger. Now we have a discussion on how the elementary potential flow can be used for any arbitrary structure. See this plot. As an intuition, we can imagine if we distribute a number of the sources and the things in the structure or on the surface of the structure, and the combination of the sources in the uniform flow would be something like this, the flow past the structure. So if so, we might have the following questions. The first question would be, do we have any mathematical proofs so we can represent the structure using the source combination, such as the uniform flow past the doublet equivalent to a flow past a cylinder or a sphere. But this problem is much more complicated than the simple potential flow. Then the second question would be how we can distribute the sources of things. And do we need to distribute the sources in the structure or just on the structure surface? And the third question would be how we can decide the strength of the sources. We will answer all these questions when my talk is more on the fluid and structural interactions for the potential flow theory. So here, some general idea would be given for the flow-structure interactions for potential flows. In fact, strict mathematical derivation can prove that the body can be represented by distributing the sources or and other singularities only on the structure surfaces. And the mathematical method have been well developed for deciding the strength of the source by solving the so-called boundary integral equation, or the method called boundary element method. The potential flow theory for long-lifting bodies, the boundary integral equations are very straightforward. However, for the lifting body, such as the airfoil or aeroplane, the Kuta-Joukowski theorem must be used.